Good day, everybody. Justin Miller, Scalar College Physics here. We are going to start looking at some coordinate systems and transformations between those coordinate systems. So, in general, we're going to stick with two-dimensional analyses, and at least for now. And what we need is some way to identify coordinate systems that we'll be dealing with and ways of transforming between them. So, coordinate systems, 2D, Cartesian and Polar. So let's start with a Cartesian system, 2 dimensions. What do we got? We got ourselves an X, we got a Y axis, and we can take any point within this space here and represent it by an ordered pair, right? So I can take some point here, call this point P, and say that this P is at some x1, y1. We can translate this down, call that x1, and translate this over, call that y1, and there we go. We got that particular point. And we can do that anywhere, once again, anywhere in this two-dimensional Cartesian coordinate system. So what we want to be able to do is also look at a polar system. We'll still throw in this xy axis, if you will, two mutually perpendicular axes. But we don't want to utilize x and y. We want to utilize polar coordinates. Polar coordinates are r and theta. So I'm going to take the same point, P, and we're going to say that this point here is at some r1 theta 1. Well, what is r1 and what is theta 1? Well, for a polar system, r is the distance from the origin to the point. There's r1 right there. And theta is the angle that that straight line makes relative to generally the positive x direction. There's r1 and theta 1. So we rotate upward an angle theta 1, and then we move from the origin to that point over a distance of r1. And that's how we signify that in a polar system. What we want to be able to do is transform between these two systems. That is, take something that is denoted in Cartesian and put it in a polar, or something that's in polar and put it in a Cartesian. This will become extremely important later on, and it'll bring us into discussing some other things. So let us look at this polar and Cartesian kind of superimposed on one another. So we could take this and stick it right on top of this. That's kind of what we'll do. We'll redraw this. We'll take our point P here. And we can note that this point P is some x1, y1, and is also correlated with some r1, theta 1. Go ahead and say that this is like an x-axis, this is a y-axis, and there's how we can signify it in both Cartesian and polar coordinates. So we can say, once again, at x1, y1, and it is also at r1 theta 1. So what we want to be able to do is transform in between those two coordinate systems once again. So how will we do that? Notice something with this. What we'll notice with this is hey, we can make a nice triangle out of all this. I could go over here, up there, over there. Got a nice triangle. I'm going to take that triangle out really quick just to make some inferences here. So we'll take that triangle out. I'm going to draw it over here. So we've got some R1, that is some Y1 there. This is some X1. And there is our theta 1. And this, of course, would be a nice right angle. And there's some other angle there, such that those three angles add up to 90 degrees. Fine. What can we say about this triangle? Well, there's a few things that we could say about it, right? We could look at, say, the Pythagorean theorem. We could get that this squared plus this squared has to be equal to this squared. So that's some place to start. X squared plus y squared is equal to r squared. Well, this gives us the ability then to say, well, if you know what x and y are, then you also know what r is. So we've got that r1 is going to be equal to the square root of x1 squared plus y1 squared. Straight up Pythagorean theorem. We know the x and y coordinates. We know what the r coordinate is. We also need to be able to get theta then. So how are we going to get theta out of this? Well, let's think about some trigonometric identities, or really trigonometric definitions. If I want to get what theta is by knowing what just x and y are, what could we do? We could look at tangent. That's all right. So we've got that in general, the tangent of theta is opposite over adjacent. By definition, right? And what's that going to be equal to in this case? That's going to be equal to y1 over x1. Opposite the angle, adjacent the angle. There we go. So this doesn't quite give us theta. It gives us what the tangent of theta is, the ratio of y to x. But we can get what theta is out of this pretty easy by taking the arctangent of both sides, right? Inverse function of the tangent is arctangent. We do to one side, we do to the other, and we've got ourselves then that theta 1 is going to be equal to arctangent of y1 over x1. So in that, we've got these two transformations here. These allow us to go from Cartesian, x and y, into polar, r and theta. Plain and simple. So that's great. That's one way to go. What happens if we want to go the other way? What if we know what r and theta are and we want to know what x and y is? Well, we can do that too. How are we going to do that? Well, let's go back to some other trigonometric identities. So we've got ourselves that we'll start with cosine. Cosine of an angle is defined as adjacent over hypotenuse. Which in this case would be x1 over r1. With that, we can multiply both sides by r1. Basically, we move this r1 over here, and we've got ourselves that x1 is going to be equal to r1 times the cosine of a theta 1. There we go. If we know what r and theta are, we know what x is. Fantastic. Lastly, we want to know what y is as well, knowing what r and theta are. So what can we do? We look to the sine. Sine of theta. That is going to be opposite over hypotenuse by definition. And what do we get out of that? That is going to be equal to y1 divided by r1. Again, multiplying both sides by r1, we've got ourselves that y1 is equal to r1 times the sine of theta 1. These four expressions there allow us to transform from and to Cartesian and polar coordinates. And what's the point with that? Well, mathematically, it's nice to be able to do. But The true point comes with what we're going to be looking at next, and that is types of quantities that we're going to be dealing with. So we'll kind of remember this here, flip that up there, and talk about this for a moment. There's going to be two different types of quantities that we deal with in this class. And you know what those are? So, we will use what are known as scalar quantities. Where a scalar quantity is represented by a number saying how much of something there is and the proper units defining what that is. So, a number representing how much something is under consideration, followed by the proper units. Used to identify that something. So I can say 10. So, okay, 10. 10 what, right? Oh, 10 meters, or 10 seconds, 10 hours, 10 days, 10 kilograms. When I throw some units on it, it has some meaning, right? Without the units, it's just a number. We don't want to just deal with numbers, because again, this isn't just a math class. We utilize math, but we're talking about physical quantities here. So a scalar quantity is some number with the proper units that identify what that number is supposed to be representing. How much of something. Some examples of that are time. Let me put in EX. Time, distance, mass, number of particles, speed. There's all sorts of scalar quantities. Temperature, it's just a number, right? Number, how much? Well, on the flip side of this, there's another type of quantity. And this particular type of quantity is going to be something that we utilize over and over and over in this course. Very important type of quantity. And that is known as a vector quantity. Well, a vector quantity is a number representing how much something is being considered. Followed by the proper units. Followed. So up until then, it just looks like a scalar quantity, right? We've got some quantity that has a number representing how much, followed by some proper units so we know what it is. But there's more. And a direction associated with that quantity. The big point being direction. A vector is a how much, but it also has a which way. To have a vector quantity, we have to have those two things. How much of something and which way is associated with that something. So what are some types of vector quantities that we may have? Well, we have different things. We have something I could say, I move 10 meters. That's great. That 10 meters is a distance. That's a scalar quantity. What happens if I say, I move 10 meters that direction? That wasn't 10 meters, but you get the picture, right? I moved in a particular direction, or I could go this way, or I could go this way, or I could go up or down. There's direction associated with which way I'm moving. That's not distance anymore. That's noted as displacement. We'll touch on this quite a bit more as time goes on, but displacement, velocity, that's how fast you're going and what direction you're moving in. Force, I can push on this table here. You can't really see the table, but I can push on this pin here. I can push it this way. I can push it this way. I can push it towards me. That's all force stuff. We'll get into that. But those are vector types of quantities, quantities that have some inherent direction associated with them. And what's nice about vectors, they tell us more information than just scalars. More information. We need to be able to keep track of things. Keep track of which way things are moving and which way they are changing their motion into. All sorts of things involving which way, vector quantities. Extremely important in physics. So this is what we want to start looking at, is vector quantities, how to represent them, how to deal with them, and I'm going to go from there. So we're still just going to be doing math here. Many of you may have seen vectors in trigonometry. Sometimes it gets skipped over, or it's very minimal. We're going to get out what we need of it and move on from there. So if you're fuzzy on vectors or haven't seen them before, we're going to go over all the vector algebra necessary for this course, and you'll be fine. And as luck would have it, it actually is really interwoven within these coordinate transformations here. And that's what we want to be able to basically extract out of this. So let's just go ahead and do that, shall we? Yes, one more. All right, so let's get to it, looking at some vectors then. So the easiest way to begin is to look at a pictorial representation of vector. Since vectors have both a magnitude, a how much, and a direction associated with them, we can use an arrow to represent a given vector. So right now we're going to keep things arbitrary. We're not going to talk about units or particular types of vectors, just arbitrary vectors here. So, a vector can be drawn as an arrow. The length of the arrow represents the how much portion of the vector is called the magnitude. The how much is called the magnitude. The direction, the arrow points, represents the direction associated with the vector. All right, so we could ultimately draw out an arrow. So I could say that we've got some vector. Let's make a straight line. There's a vector right there. The length of this vector is scaled to represent its magnitude, its how much, the quantity associated, numeric value, and the direction that it points is the direction. So there's the magnitude, and we can represent the direction that it points measured with respect to some sort of other reference direction, typically the positive x direction. So we could call that theta. Is the direction. We take this vector and we have one that's half the size pointing in the same direction. It has half the magnitude, half the numerical quantity. We change the direction of it, we change the angle. So this is typically how we want to start looking at vectors in general, is just represented as a magnitude and a direction. A how much and a which way. How much, which way. Those are the two things that we always want to start thinking about with respect to vectors. How much, which way. All right, so going on with this, what we need to do now is sort of look at different ways of mathematically representing vectors. And we'll make a connection between the pictorial view and the mathematical symbolic representations. So we can have that a vector can be written as an arrow, as a letter with a hat on top of it. A, and this is called A hat. This little part right here is the hat. It's supposed to be like an arrow to remind you that this is a vector quantity, that it has some sort of direction associated with it. If we just write the letter A, well, that's just some scalar quantity. A hat is a vector quantity, so we'll call it A hat, or B hat, or C hat, or D hat, or E hat, or F hat. Depends what we're trying to reference here. This is just arbitrary, but we'll have some letter with a little hat on top of it. We'll call it A hat. You'll find in books that oftentimes this little script for an A hat is hard to produce, so they'll just use bold print. Bold print letters in books represent vector quantities. So you've got to be a little bit careful of that. It's either got a hat on top of it, or it's bold print, then it's a vector quantity. It has a magnitude and a direction. So that's how we can write out or illustrate, not illustrate, but say that we're talking about a vector quantity. And it can be a given vector, excuse me. in 2 dimensions can be represented in 2 general ways. We're sticking with 2 dimensions. Really, it goes with 3 dimensions as well, or 1 dimension for that. We'll just stick with 2 dimensions. And the different ways that it can be represented is noted to be as a magnitude and direction, which would be like A hat is equal to the magnitude of A hat. It looks like absolute value signs. This is referencing magnitude, the how much, at some theta sub A. So if we draw out a vector, we'll do purple again, draw out a vector. What we said was the magnitude here, that is this. If this is some vector A hat, the length of it is scaled to be the magnitude, the how much, if you will. And then we've got some theta sub A that's generally, again, referenced with respect to the positive x direction. So this is what we do. This is magnitude. This is the direction. So that's one way that we can represent a vector. Magnitude and direction. How much, which way. We can also represent a vector in what's known as unit vector notation. Unit vector notation, it breaks the vector down into its components that are mutually perpendicular to one another. Typically we're using x direction and y direction, perpendicular to one another, so we can write this. A hat is equal to a sub x I hat plus a sub y j hat. So this looks a little bit different than this, right? Well, it's a different representation of it. But these 2 ways can express the same vector itself. It's 2 different forms. So what we need to know is what is this ax, this ay, this I with an upward arrow and j with an upward arrow sort of look to them. So ax and ay are the components of the vector in the x and y directions, and I hat and j hat are the unit vectors in the x and y directions squeezing that in respectively. So I hat says, oh, that's not says that. We'll do x direction. That's what it means. It's telling us specifically x direction. So this is the component that's in the x direction. We say, well, subscript with an x. Yeah, that's the x component. But this makes sure that we're talking about a vector quantity here. Something that has a direction associated. Just not an amount, but a direction. So this is the x direction, I hat, and j hat is the y direction. And if we wanted to go into 3 dimensions, we can throw in a k hat, which would be the z direction. But we use I hat and j hat. So if you haven't seen I hat and j hat before, maybe you've seen x hat and y hat. We use I hat and j hat so that we don't start needing to get confused, with the x's and the y's and directions and variables and all sorts of things. I hat and j hat's a little bit easier to sort out. And these upward pointing arrows here, parts of arrows, tell us that those are unit vectors. They have a magnitude of 1. Ultimately, they're just saying in that particular direction. So we can break a vector down into its components. Some amount in the x direction and some amount in the y direction. So what does that look like? Do a little erasing here. Just draw it out again. So we'll go ahead, take that same vector a hat. So we've got our vector a hat right there, and what we can do is we can look at the projection of this vector onto the x direction and the projection of the vector into the y direction, and we can form the components from that. So we can look at this like this. We can take this straight down, take this over, and this would be the x component, this would be the y component. This is a sub x in the x direction, a sub y in the y direction. I hat, j hat, which forms the total vector a hat. So this is how we can look at the components. So with this, what we want to be able to do is express any given vector in either unit vector notation or as a magnitude or direction. And we're going to find that sometimes we've got to switch back and forth a whole bunch. Just depends what we're doing with them. But there are two different ways of representing the same vector. So what we could do with this is just start drawing in really these other two quantities here, the magnitude and the direction of this true vector a hat. So what do we have? We've got ourselves, there's the magnitude right there, and there's the direction right there. So what happens if we want to make some sort of correlation between these four different quantities? The x, the y, the theta, and the magnitude. Well, it looks kind of similar to what we had with respect to the transformation between Cartesian and polar coordinates, does it not? Yeah, it does. It looks like exactly the same sort of thing. It's got different looking quantities here, but it's the same thing that we just looked at. So let us do this. Given that we have, say, the components of a vector, could we get what the magnitude and the direction are? Yeah, the magnitude's like the length. It's like the hypotenuse, right? And the direction is just the angle with respect to, well, the positive x direction, which is typical. So what can we do with this? Well, we can write out that the magnitude of a hat is equal to the square root of a sub x squared plus a sub y squared. That's just the Pythagorean theorem. A sub x squared plus a sub y squared is equal to the magnitude of a squared. Take the square root of both sides, and that's what we've got. So this is how we could get, again, the magnitude based upon the components of the vector in 2 dimensions. And what else could we do? Well, we could notice that the tangent of theta sub a would be opposite over adjacent, which would be a sub y over a sub x, which would then give us that theta sub a is equal to the arctangent of a sub y over a sub x. There we go. If we know what the x component is and the y component, we take the arctangent of the ratio of the y to the x, and we've got ourselves the angle with respect to the positive x direction. Be a little bit careful with this, but in general, that's what we've got there. So this gives us, again, the ability to get the magnitude and direction given the components of the vector. Sometimes we'll have the magnitude and direction, and we need the components. So how are we going to get those? Well, we just look to sine and cosine. So before I get ahead, just to make sure we're on the same page with that, we've got the tangent of theta sub a, again, opposite over adjacent, a sub y over a sub x, which then take the arctangent of both sides, and we get this. We've also got the cosine of theta sub a would be adjacent over hypotenuse, which would be a sub x over the magnitude of a, which we could then take the arc cosine of both sides. No, excuse me, we don't want to do that. We're trying to get a sub x, which we could then multiply both sides by the magnitude of a, and we can get ourselves that a sub x is equal to the magnitude of a times the cosine of theta sub a. And lastly, we've got ourselves the sine of theta sub A is opposite over hypotenuse, A sub y, over the magnitude of A, which then again multiply both sides by the magnitude of A, and we've got ourselves that A sub y is equal to the magnitude of A times the sine of theta sub A. And there we go. So I'll go ahead and put down where theta sub A is measured relative to the positive x direction. If you measure it relative to, say, the negative x direction or the y direction, it changes some things around. We generally just stick with measuring things relative to the positive x direction. You don't have to worry about stuff. So this is how everything kind of falls out right here. These 4 expressions there allow us to go back and forth between unit vector notation and a vector as a magnitude and a direction. And we will be doing lots of that. So at that, I think we're in a good position here to go ahead and look at a couple little problems involving some of this, and then we'll move on. There's more to do with vectors, but we'll start out looking at this stuff. All right? All right.